Imagine someone is trying to break into your system by repeatedly testing it over and over, looking for weaknesses. They keep running these tests, hoping to find something they can use to take over your system. What if we could slow them down? So every time they try something, we make them wait or block for a bit. So instead of getting faster, they end up wasting their time. That is what we want to do here. Slow down those who are trying to find weaknesses so they cannot reach their goal easily and give up. So basically so in this presentation we will show you how we can do that exactly, making it harder for attackers to find and exploit problems in the system. So counter fuzzing will be the topic of our presentation. So before starting, let's go over the agenda of today's presentation. First, we're gonna start about what is fuzzing and the definition of fuzzing, and then why fuzzing is important and why we're doing so much time about fuzzing, and then what are some malicious use cases of fuzzing, and then we're gonna dive deeper into counter fuzzing and some background and related work regarding counter fuzzing techniques, and then we're gonna talk about some available architecture for counter fuzzing techniques, and then we're gonna present our contribution for the project and the design for that, and then some implementation details and result after running our experiment, and then summary, takeaways, and future plans that we aim to extend for the project. So let's start. What is fuzzing? Fuzzing basically is an automated testing technique where we feed random or mutated input to a program in an attempt to discover unknown vulnerabilities. It is commonly used to test third-party code, and it is an effective way to find bugs, memory leaks, and other vulnerabilities. So basically, we can ask ourselves why fuzzing is important, and the answer for that question is, first of all, it is unpredictable process. So fuzzing allows us to simulate real-world data, which often behave in ways we cannot predict. And second, for large programs, it is not practical to manually analyze every possible input, and static analyzers often perform suboptimally. And essentially, fuzzing allows us to automatically find vulnerabilities that could otherwise remain hidden, including zero-day vulnerabilities. So there are some uses of fuzzing where attackers use them maliciously. So basically, some attackers can use fuzzing to find vulnerabilities in third-party or closed-source software. And attackers use fuzzing to discover zero-day vulnerabilities, as I just said. So basically, these discovered exploits are sometimes sold on black markets for profit. And also, lastly, fuzzing is valuable because it does not require access to source code, just the binary is enough. And a famous example for that is 2017, the WannaCry ransomware attack exploited a vulnerability. It was actually discovered through fuzzing technique. So if this technique have been found and patched from the beginning, the massive global disruption could have been avoided at all. So now we can think while fuzzing plays a key role in identifying vulnerabilities, it is also a powerful tool for attackers. So the question might be, how do we stop fuzzers from making our system their target? And the answer for that is basically counter fuzzing. So now, after understanding attackers can use fuzzing for unethical activities, some effort have been done to mitigate the malicious use of fuzzing, which is called counter fuzzing. So what does it mean again? It refers to techniques that prevent or disrupt fuzzing attack by making fuzzing less effective and more resource intensive. There are some counter fuzzing techniques, but such as there are some ways to detect fuzzing. We have passive methods and active methods. Both methods are actually aimed to identify when a program is being fuzzed, but they differ in approach and implementation. So for the passive methods, its main goal is to detect fuzzing without affecting normal execution. There are some methods for doing that, such as time gap, which detects delays caused by fuzzing, and second, like file monitoring to track rapid file creation by fuzzer, and the EIC, which basically to detect anomalies in instruction method. And there are some mitigation efforts to like prevent this fuzzing attack, such as adding delay to hinder fuzzers and terminate the program or trigger fake errors. And for the active methods, it is basically its main goal is the fuzzer are misleading by modifying the program, such as like methods for doing that is inserting misleading code blocks, which is called fake blocks, and redirect fuzzer to random instruction like the landing space, and minimize fake block size to reduce the overhead. And for the mitigation techniques, we have jump instruction to reduce the performance impact, and spraying to distribute fake blocks to reduce hash collision. So there are other like available framework in the literature to having for like to work as like counter fuzzing. First one is the speed bump, and this technique basically introduces delay during fuzzer. Some proofs for that is slow down fuzzer. It makes fuzzing much slower, so it becomes very time consuming and less effective, and reduces fuzzing efficiency. Fuzzers basically struggle to find bugs because they take too longer to run. Some cons for that is a delay for normal users. It could cause a slight delay in normal program execution, and it is only useful against fuzzers, so it does not protect against other type of attacks. Okay. And for like the branch trap, it is basically a technique which is to confuse fuzzer by misdirecting their path. So the fuzzer go down the wrong path and wasting their time on areas that do not matter. And another thing is it stops fuzzers from quickly finding bugs by interfering with how they work. And some cons for that is false result. It might make fuzzers think they found a problem where there isn't one, and increase program load by adding traps can make the program a bit slower, especially for large programs. Last thing we have is the anti-hybrid. Is basically it targets hybrid fuzzer, especially those using symbolic execution. It works by like a stopped symbolic execution by blocking the part of hybrid fuzzing that help fuzzer understood complex program behavior. Some cons for that, it is hard to implement because this technique is difficult to set up and apply to any program, and it only effective for hybrid fuzzers, so it is not as useful as some other techniques for any other types of fuzzer that don't use symbolic execution. So for our contribution, we basically have we basically propose a novel counter fuzzing solution that combines the strengths of existing solution technique while eliminating their drawbacks. Our solution is designed with the following key characteristics. First, no slowdown for normal use. Our solution targets fuzzing at temp, especially ensuring that regular user experience has no noticeable delay or performance degradation. Smart execution control. We use dynamic execution monitoring to only delay fuzzing at temp when abnormal behavior is detected. This ensures a smooth performance behavior for legit user. Third thing, our solution is easy to implement and does not require deep integration with the fuzzing framework, meaning that it works across different fuzzing setups without a heavy implementation burden. And we ensure that our solution imposes very little computational overhead, preserving the program efficiency while still protecting against fuzzing attempt. And last thing, we ensure that it remains undetected by fuzzers who are often trained to identify and bypass standard counting fuzzing method. And now Rahul is going to talk about high-level design for our project.
Right. Thank you, Danya. Now I'll be talking about the high-level design of our project and how our implementation ensures counter fuzzing. So here's a high-level overview. We have a protected binary which we generate using our script, and the protected binary basically just checks if the binary is being fuzzed or not. So we continuously monitor if the program is being fuzzed by examining its behavior, specifically looking at execution frequency. I'll talk more about that later on. And if the program is being fuzzed, we introduce latency, and this latency will slow down the fuzzer, making it less efficient, and ultimately the attacker might give up. The execution control also ensures that normal user operations are unaffected. So the design ensures that the way how we generate the new binary will make sure that normal operations run as it is. So the way how we detect fuzzing is, first of all, as I talked about before, we examine the execution frequency. So usually fuzzers execute the target binary frequently within a short time. And what we do is that with our binary, we ship a daemon process. So as soon as the binary runs, it spawns a daemon process in the background, which patrols a temporary file. It locks the file and it deletes them to manage a particular threshold. So, for instance, say if the fuzzer exceeds a threshold, say 60 times. So, say if the binary is called more than 60 times, the binary the binary will try to mislead the fuzzer with artificial crashes, and in some cases even abort the fuzzer. So and as a mitigation technique, we also randomize function calls. So the way how this works is that we try to transform normal function calls to random function calls through shuffled function pointer tables. This is on a source code level, and before compiling the binary, we run the script on the source code, which modifies the source code, and then we compile the binary. So what these modified function pointer tables will do is that they will point the actual function call to hundreds of fake functions per real function, and each fake function will be simply filled with junk instructions, which can mislead the fuzzer and cause a lot of it will induce a lot of time delay. Okay, now let's dive deep into the implementation. So as we talked about examining execution frequency, the first part is to inject a daemon process. So what we do is that in the original source code, as soon as we run our anti-fuzz script, what it does is that it will try to locate the main function in the actual file in the target source code, and it will introduce a function, a create daemon function, which you can see here. This is like a very simplified pseudocode, but what it basically does is it touches a temporary file on the system and keeps on tracking the access of the file. So if the binary is being fuzzed, if the target binary is being fuzzed, the file being accessed will be very frequent. The access count of the file will be very frequent, and this way we will be able to detect that our target binary is being fuzzed. So this create daemon function is injected into the original source code while by detecting the earliest include statement, and that's where we just inject our code. Once we do that, we have a temporary output file, and we then this temporary output file can be compiled, and we have a new protected binary. This protected binary, as I've told you before, it executes two processes. One is the parent process, which is the normal program execution, and the other is the child process, which is forked, which is just basically like a fork from the parent process. This child process will do all monitoring for the temporary file. It will write access count to the temporary file. It will sleep for 30 seconds to trick the fuzzer, and it can even abort the fuzzer. And once done, it can remove the temporary file. Um, and now coming to the part where the function calls are randomized. So here I have a very simple example where we're talking about a very simple function which just adds two numbers. This is all for illustrative purposes. What we do here is that we generate a type def for the function, which is basically just like a definition for storing the function pointer. And what we do is that we generate these random functions, which are just basically like fake functions with a bunch of fake instructions. These fake instructions could be a bunch of no ops, unnecessary jumps, or jumps which are creating long cycles. Uh, and once the list of fake functions is generated, we fill these in a function pointer array. And so now what will happen is that the original function is transformed into a random array of functions, and it will call the real function very randomly, and it will keep, otherwise it will just keep on going through these random function calls. Now this introduces a time delay again to confuse the fuzzer. So coming on to the evaluation, we had a test bed setup which was running Ubuntu 24.04, one of the latest kernels, 6.8, and we were running the test on a 12th gen Intel Core CPU with 20 cores. These are 20 logical CPU cores, and all of the compilation was done using GCC 13.3. So the steps for experiments are, so we from the Forte Fuzzbench repo, we picked the libjpeg binary. Libjpeg is basically a free C library for reading and writing JPEG files. And what we try to do is that we try to patch one of the source code files in libjpeg by adding these fake blocks. And the file name in this case is djpeg.c. This is the entry point file and has the main function. And once we patch this file, we compile both the original and the patched binaries. The original binary is compiled before modifying the file. And then we perform the test on both the binaries with AFL. AFL is a very famous fuzzer, and its AFL stands for American Fuzzy Loop. And we run the fuzzer for about 30 minutes to compare the results on both the binaries. So yeah, let's jump into the demo. So here I have the demo. If you'll see what's happening here is that I'm trying to compile the libjpeg, like the vanilla libjpeg, without modifying the file. And once that is compiled, I'm going to copy the binary into a folder just created for benchmarks. The folder is called bench. And once copied, now what we're trying to do is that we're trying to run our script, which is called codeinst.py, and we're trying to modify the entry point file, which is djpeg.c. The argument you'll see here are 10, 3, and 10, which specify 3 is basically the number of functions to target, and 10 is basically the number of fake blocks which we want to generate. Once that is done, you'll see output.c, the file which is generated. So what we do is that we remove the original file and we replace the original file with the file which we generated. So now when we compile, you'll see a new binary is generated, and we're copying it again to the bench folder, but this time we call it antifuzz djpeg, so that we can differentiate between the two binaries. Now we'll cd into the bench folder and try to run AFL on both these binaries. So this is basically the AFL command for the. So you'll see that I'm trying to set these environment variables, which basically just skip crashes and skip CPU frequency, because in our case the binary induces a time delay too slow that we don't care about crashes and we don't care about enabling CPU throttling. So we're just setting these environment variables for the sake of simplicity. So first of all, we try to fuzz the original binary, and we try to run the fuzzer, and the fuzzer is running on the original binary. Parallelly, I'll again start a new SSH session into the same machine and try to fuzz the modified binary. So we're going into the bench directory, and we'll change the output directory so that we can distinguish between the results. And now we're going to fuzz the modified binary, which is called antifuzz djpeg. since a temporary file was already created, it aborted the fuzzer. So I'll just delete the temporary file and run the fuzzer again. So yeah, now the fuzzer is running on both the files. So as you can see, the cycles done in case of the original binary are way over 200 in just less than a minute. And we can see the execution speed is around 1992 cycles per second, and there has been already 144k executions in under a minute, and only 14 timeouts for all these 144k executions. Now, when we compare this to the modified binary, you'll see that the execution speed is way less than the original binary. It's just 13 executions per second, and only 290 executions have been done as compared to the original binary. And you can see a lot of these executions lead to timeouts or hangs. So, which can prove that our modified binary works. So now we'll deep dive into these results again. So as shown in the demo, we could just show a small demo, but these are the results from a 30-minute benchmark which we did on both the binaries. As you can see, we also have the results here. As you can see, after running fuzzer on both the binaries for 30 minutes, the original binary made up to 12k cycles, while the protected binary could just do only 338 cycles. And there were around 85k timeouts, which indicate that our patching technique was able to introduce a time delay. And you can see this also in the total executions, and the execution speed was also affected. So I'll give it back to Donia to summarize the takeaways.
Thank you, Rahul. So let's try to summarize what has been going on throughout the whole presentation and some takeaways we already had now by examining the whole process of fuzzing. So first thing, like to summarize, fuzzing is widely used technique to identify vulnerabilities in software by testing it with random or mutated inputs. However, fuzzing can be exploited by attackers to find vulnerabilities in third-party software, making it necessary to implement counter-fuzzing techniques. So the existing counter-fuzzing methods such as speed bump, branch trap, and anti-hybrid are effective but have limitations such as performance impact on regular users, false positives, and high storage cost. So basically, consequently, we propose a new counter-fuzzing solution which is designed to address these limitations by providing minimal or almost zero impact or on normal execution, adaptive misdirection, and low storage overhead, make it highly effective without affecting legitimate users. So like some takeaways we can have from this stuff is fuzzing and like the associative risks. Fuzzing basically is as a crucial tool for finding software vulnerabilities, but it can be used by attackers to exploit and patch software, as we explained like at the beginning of our presentation. And the existing solutions, for example, current counter-fuzzing techniques have their drawback and limitations such as performance issues, false positive, and high storage demand. Our proposed approach, it offers minimal impact on regular users, avoid false positive, and it is working against different fuzzing techniques, including like hybrid fuzzing and any type of attacks. Our solution is compact, efficient, and adaptive, offering a stealthy defense that adjusts to the fuzzing environment. This ensures fuzzing cannot bypass it easily, which is make it like undetectable as a result. So our new approach provide a more effective and scalable way to defend against fuzzing. This improves security while maintaining system performance. So for future work, we have actually like some nice, exciting ideas to like extend this work. So we aim to extend our work by supporting handling like false positive in the detection, because sometimes when we were reading in the literature, some framework has basically reporting false positives, which means that some framework like are reporting that the program is being fuzzed. However, this was not the case. Maybe it was just like high CPU load or some sort of like hardware specific stuff. But in our solution, we didn't like handle, or we didn't examine to what extent we have false positive in our idea. So as a future work, we aim to handling like such scenarios. And also our approach, applied we only included the passive detection techniques, but we believe that we can still use some features and characteristics from the active detection techniques. So we believe that the best case scenario is basically best of the two worlds, which is to be hybrid approach, to have both the characteristic of passive and active detection techniques. And last but not least, we need to apply these techniques to well-known fuzzers other than the AFL1, such as Hong fuzz, cluster fuzz, and etc. I think due to the time constraint, we only apply it to one fuzzer, but it will be interesting to apply it to more fuzzing techniques in the industry and in the literature, to prove that our fuzzer is actually like working on different different fuzzer. And we also need to like ensure that it provide like the minimal impact of normal execution for all of these fuzzers. So I think that's it for our presentation. Thank you so much. And if anyone has any question, you can definitely ask or like reach out to us through the email.
Thank you.
Thank you.